All right, we are back with section 2.3, applications of systems. The third video of the week. What? We're getting crazy. But this one is more of just practice for what's coming next week. Something that's going to be a lot more difficult if we just completely skipped over this. So because of that, we are just going to skip right to example 1, and we're going to practice just writing equations, this time in two variables, given some information, given a little example problem. So you sold two different types of wrapping paper for your band fundraiser. One type sold for $6 a roll, the other sold for $8. You collected a total of $92 for the 14 rolls you sold. Whoa. How many of each type we sold? Gotta love a good old English grammatical mistake here. How many of each time were sold? Fix that if you really want. But first of all, what are we trying to find? We want to know how many of each type. So let's start by defining two variables. Let's call X type 1, Y will be type 2. So just a little hint for you. Anytime you see money involved, usually those three numbers are going together. So we know our total money sold, total amount of money made, I should say, was $92. So we're going to start with 6. 6 for the first type. $6 for the first type. We don't know how many of the first type, so we got to go 6 times X. Again, we don't know how many we sold of that first type. Plus 8 times Y, however many we sold of the second type, gives us $92. The only other piece of information we have is that we sold 14 total rolls. So if we take the number of type 1 rolls plus the number of type 2 rolls, we get 14 total. Now again, the whole idea of this lesson is just to work on the setup. If you want to go ahead and solve, I know you guys get bored. You love doing math when you're bored. Go ahead and finish solving this in any way that you can remember. Otherwise, we are moving on. Katie has 70 coins. That's a lot of nickels and quarters in her piggy bank. So lucky. That costs a total of $13.90. How many of each coin does she have? So again, we want to know how many of each coin. Let's define some variables. Now you can be creative if you want. You can use N for nickels, Q for quarters. I'm just going to go ahead and stick with X and Y. So X is the number of nickels. And I promise that is not hashtag of nickels, that is numbered. The number of nickels. Y is the number of quarters. So I mentioned in the last example, anytime you see money, usually those values go together. But I only see one money value. And I know that the total of our coins is $13.90. I do need some other money values, though, to go with that. But you kind of have to think outside the box on this one to come up with them. And it starts with the value of a nickel. The value of a nickel is 5 cents. We would write that as 0.05. So the value of a nickel times the number of nickels. We don't know how many, so we'll just call that X. Plus the value of a quarter is 0.25 times Y, because again, we don't know how many quarters. So if we take the value of a nickel times the nickels, plus the value of a quarter times the quarters, we get the total of $13.90. The other thing we know is that there are 70 total coins. So if I take the number of nickels plus the number of quarters, I get 70 total coins. So there you go. Very similar setup. And that's going to be with any time you see a problem that's dealing with how many of each type, types of quarters, how many types of wrapping paper, whatever, how many apples, how many oranges. Similar setup as these two examples we just did. When you compare two things, what you want to do is write an equation for each thing you're trying to compare. So in this example, we have cable 1. Let's scoot that down. And we have Midco. So we're going to write an equation for each one of these when you compare two things like this. And again, if you want to go ahead and solve, be my guest. But well, first of all, I guess we need two variables. Let's go X and Y again. It looks like we are looking for how many hours would you need to use the internet per month for the services to be the same price. So I need to know, first of all, how many hours. So let's go, X can be the number of hours. And again, be creative if you want. If you like H for hours, that'd be my guess. Y is going to be, well, we want to know when they're the same price. So you can think of it as price or cost or, whatever. I'll go price this time. So, cable 1, the price for cable 1 is going to equal, it says $12 per month. Now, we're assuming it's 1 month. It probably should say that in the example. So, we know how many months. We don't want to put a variable with that number. But it does say plus, therefore the addition, $2 per hour. We don't know how many hours, so there's where our X is going to go. So, that's our equation to represent cable 1. Midco, the price of Midco is going to equal, it says $27 per month, but again, it's 1 month, no variable needed, plus 50 cents per hour. And again, we don't know how many hours, so we have to use the variable X. So that is our setup for example number 3. Now I'm going to go ahead and just kind of scroll past another, 2 more examples of comparing two things, and jump right to these distance and rate problems. These seem to give people the most problems, so I want to make sure to cover at least one. So we have a plane traveling 540 miles in 6 hours with a headwind, and coming back, it only took 5 hours for that same 540-mile trip. Find the speed of the plane and the speed of the wind. So here it's telling us what 2 things we need to find very explicitly, just right in front of us. So X is going to be speed of the plane. Goodness. Speed of the plane. Y is going to be speed of the wind. Okay, now when you start these problems, you want to figure out your miles per hour going one way and your miles per hour going the other way. Kind of like the speed of the plane, including the wind, the speed of the plane with the wind pushing it. So in order to do that, you're going to take your total miles. So we'll go headwind here. To figure out the average speed driving rate, flying into the wind, you're going to take 540 divided by 6. The miles divided by 6 hours, that is going to be an average of 90 miles per hour. It's an incredibly slow plane. But with wind blowing into it, it's going to be going a little slower than you'd expect. So now we'll go, coming back, the wind was blowing the plane, closer to the destination. So it's going to speed up a little bit. That's why it took an hour less. So to find the average speed coming back, we'll take the same 540, but this time we're dividing it by the 5 hours it took to get back. And we end up with 108 miles per hour. So here's why that's useful. When we write these 2 equations down, the first equation, we're going to take the speed of the plane minus the speed of the wind, and that's going to give us an average of 90 miles an hour because the wind is slowing us down. So it's taking off the speed of the plane. So the speed of the plane was 9 miles an hour, or 100 miles an hour, and the wind was 10. It's slowing us down, so we have to subtract the speed of the wind. But going back, we're taking the speed of the plane, and this time we're going to add the speed of the wind for an average of 108 miles an hour because we have the wind pushing us along. Let's do one more here, example number 7, and then we'll call it a lesson. Same idea. We have a passenger plane, took 3 hours to fly 1,800 miles in the direction of the jet stream. So that means it's pushing, it's pushing the plane. The return trip against the jet stream took an extra hour. What was the plane speed in still air and the jet stream speed? So speed of the plane and the jet stream. Again, let's go. X will be speed of plane. Y will be jet stream, just another way of saying wind, so I'll call it speed of jet stream this time. Again, we want to find, on average, the miles per hour going both directions. So, we'll go with the jet stream. We're going to take the 1,800-mile trip, divided by the 3 hours for an average of 600 miles per hour. Coming back, we're taking that same 1,800-mile trip, but this time it took 4 hours, a little bit longer, for an average of 450 miles per hour. And then the setup's the same. So if you take the speed of the plane plus the speed of the jet, or the wind, essentially, we get an average of 600 miles per hour. If I take the speed of the plane and subtract the speed of the wind, or the jet stream, I get an average of 450 miles per hour. And that's it as far as setups go. We will get more advanced, adding another variable and another equation next week.